The goal of this paper is to construct a machine learning model that is suited to the encoding of raw audio, both in supervised and unsupervised settings. Historically, feature learning in speech recognition or music information retrieval has not been formulated in the raw waveform domain, but rather on top of some predefined time-frequency representation, which arises from auditory filterbanks. Here we show three such filterbanks: ANSI, third-octave, MEL, and Gammatone. Line color denotes the resolution of the filter as measured in octaves below the critical sample rate. In this context, the past decade in machine listening research has witnessed a rapid diversification of scope, with many fruitful applications in animal conservation, urban planning, industry, and healthcare. With those applications, and unlike speech or music, we typically lack the domain-specific knowledge that would be necessary to tailor the parameters of filterbank design ad hoc. This shortcoming motivates us to turn the time-frequency representation into a trainable component of the convnet and optimize it jointly towards a data-driven learning objective in a so-called end-to-end fashion. Arguably, the simplest kind of trainable filterbank is a layer of one-dimensional convolutional neural network, or convnet for short. Under this perspective, the learned kernels of the convnet may be interpreted as the finite impulse responses of auditory filters. In previous years, the replacement of filterbank design by filterbank learning has been occasionally successful in the very few use cases where data were abundant and had limited intra-class variability, say English speech and solo piano music, for example. Still, authors have repeatedly pointed out that, compared to spectrogram-based convnets, the training of waveform-based convnets causes numerous frustrations in practice. Filters tend to be noisy, out of phase, or poorly localized in the Fourier domain. In light of these findings, we concur with Schlüter and Gutenbrunner, who recently declared that, quote, "the quest for learnable audio convnet is not solved." The destination of this quest would be a neural audio model that would outperform filterbank design on difficult machine listening tasks given limited label data. In this article, we propose to take a step back and formulate a simpler question, which might get us part of the way there. Before we try to outperform an auditory filterbank, can we replicate its responses with a neural audio model? To answer this question, we are going to perform teacher-student knowledge distillation, where the teacher is a predefined auditory filterbank, lambda, and the student is our neural network of choice, phi, with trainable weight w. The learning objective is the cosine distance between the squared magnitudes of the teacher and those of the student, on average over an unlabeled corpus of natural audio signals, x. This objective rewrites as a Euclidean distance between L2 normalized responses, here denoted with a tilde decorator. Note that this is a non-convex objective. Thus, under our protocol, gradient-based knowledge distillation resembles the training of a deep neural network, even though our student model phi w contains a single linear layer. The first candidate for the student model is a simple time domain filterbank, or convnets for short, and here each filter has a complex valued finite impulse response of length 2L plus 1 and stride 2 to the power j. Each coefficient in the impulse response is a neural network parameter. Next, we evaluate a parametric filterbank in which each finite impulse response is subject to a Gabor parametrization, hence the name Gabor 1D. Only the amplitudes, center frequencies, and bandwidth of each bandpass filter are independently learnable. This architecture is less expressive than convnets, but it guarantees a near-optimal time-frequency localization for all learned filters. Thirdly, we present a novel contribution, an architecture we call multiresolution neural network, or MuReNN for short. The key idea is to operate in two stages. First, multiresolution approximation, and second, per subband strided convolutions. Only the latter stage is trainable, whereas the former stage is accomplished with wavelet design. Denoting by lowercase j the octave index, stage 1 is equivalent to a convolution between the input signal and the wavelet psi j, followed by subsampling by a factor of 2 to the power j. In the interest of time, I will gloss over the exact design of the multi-resolution approximation which we have used for this paper. Suffice it to say that it's known in digital signal processing as the dual-tree complex wavelet transform, that it can be made efficient thanks to a recursive filtering and subsampling scheme, and that we have released a differentiable implementation in PyTorch as part of the Gammatone consortium. Stage 2 is very concise and entirely relies on the standard library of PyTorch. At initialization, we build a different conv1d operator per octave with the appropriate number of filters, stride, and kernel size. At prediction time, we simply loop through octaves and apply the corresponding conv1d operator over both the real part and imaginary part of the complex valued subband. We square and sum the outputs to obtain a squared magnitude response at the desired resolution. We assemble a benchmark of 4 knowledge distillation tasks, each representing a different domain of audio content analysis: synthetic sine waves, speech from North Texas vowel dataset, music from Tiny Studio Online dataset, and urban from the Sounds of New York City urban sound tagging dataset. In each domain, we find that MuReNN outperforms Gabor 1D and conv 1D in terms of goodness of fit on previously unseen audio data. Furthermore, on the loss curves, we observe that convergence is relatively fast and robust to random initializations of neural network weights. We supplement this benchmark with a qualitative analysis by visualizing the real part of learned filters. Here, we show the case where the input data consist of spoken English vowels and the teacher is a Gammatone auditory filter bank. On the left column, and consistently with previous authors, we observe that the filters learned by conv1d retain some broadband noise in their impulse responses. In the middle column, we see that Gabor 1D learns the correct center frequency for each filter, but is hampered by the discrepancy between Gabor and Gammatone in terms of temporal envelope, particularly at high frequencies. In the right column, we find that MuReNN closely replicates the outline of the teacher filter bank, and so at all frequencies, up to an arbitrary phase shift, which disappears in the magnitude spectrogram. Not only does MuReNN fit auditory filter bank better than conv1d or Gabor 1d, it also has a better memory footprint and computational complexity. An analysis of algorithms reveals that to cover a large receptive field of size n, MuReNN needs in proportion of log n trainable parameters and in proportion of n log n multiply add operations. Therefore, MuReNN is suitable for embedded computing on resource-constrained devices, such as battery-powered or solar-powered autonomous sensors. In conclusion, we must consider the interplay between neural network architecture and iterative optimization. Simply put, saying that a convnet can fit an auditory filter bank is not equivalent to saying that it will fit the auditory filter bank. With MuReNN, we report better goodness of fit on 4 knowledge distillation tasks. And let me insist that for those tasks, the global optimum of MuReNN is probably worse than the global optimum of conv1d. But in practice, MuReNN converges to a better local optimum due to the effect of random initialization, finite training data, and stochastic gradient descent. This empirical finding suggests that the multi-resolution approximation offers a powerful form of inductive bias in the sense that the filters which are learned by MuReNN inherit the property of wavelets, compact support, vanishing moments, Hilbert analyticity, and so on. All that being said, a noteworthy limitation of MuReNN is that one needs to predefine the number of filters they expect to find in each octave subband. So, just to be clear, we're not entirely doing away with domain knowledge here. Lastly, today's talk was mostly focused on explaining how MuReNN works, but if you're interested in understanding why, let me invite you to read my latest archive preprint and meet me at the same workshop on Thursday to discuss the theoretical underpinnings of deep learning in the raw waveform domain. Thank you.